All right, welcome everyone to another deep dive. Today we're tackling something that's, well, kind of crucial in the world of data, keeping things running smoothly even when, things go wrong. We're talking multi-site high availability and disaster recovery. And to really get into the nuts and bolts of it, we're focusing on, we're looking at it through this really detailed exploration of IBM Storage Scale. But, the concepts we're going to be talking about today, they're not limited to just one specific technology, right? They're applicable across a wide range of solutions. And actually, speaking of solutions, let me take a moment to thank our sponsor for this deep dive.
Absolutely. We couldn't do these deep dives without the support of companies like Stonefly.com, who, by the way, are real pioneers in providing these really robust and reliable storage solutions.
So for those of you who might not be familiar, stonefly.com offers like a whole suite of solutions. We're talking SAN, NAS, S3 object storage, backup, disaster recovery, cloud stuff, you name it. And they've even got advanced AI and security applications and technology baked right in.
And the really impressive thing is that Stonefly has been doing this for over 2 decades. So they really understand how important data availability and business continuity are. Like, it's not just a buzzword for them, it's literally in their DNA.
So if you're interested in learning more about how Stonefly can, help your organization keep its data safe and sound, reach out to them at sales@stonefly.com.
Absolutely. Their team's really great, very knowledgeable and helpful.
Okay, so back to our topic. So the first thing we need to wrap our heads around is this idea of a stretched cluster. It's basically like imagine having your critical systems running in more than one place, at the same time. This kind of design, which by the way, Stonefly has tons of experience with, it builds in resilience from the ground up.
Right, because it's all about distributing those critical systems. And honestly, that's like one of the fundamental principles of high availability. You don't want to put all your eggs in one basket, so to speak.
Yeah.
And the network connecting these locations, that becomes absolutely critical.
Yeah, the network is definitely the backbone of all of this, especially if you're talking about systems that need like immediate consistency, where a change in one location has to be instantly reflected in the other.
Exactly. And for that, you're going to need a network with very low latency. We're talking round trip times, ideally under 10 milliseconds.
Hmm.
And, things like physical distance and the number of network hops between the sites, those play a huge role.
Right, right. And then, of course, you have to think about failure domains. It's like identifying anything that could potentially cause an outage, right? Could be a server rack, a power supply, a network switch, even an entire data center.
And Stonefly's philosophy, which I really like, is all about isolating these potential points of failure. So if one goes down, the whole system doesn't crumble. It's
Yeah.
about building that redundancy and resilience.
Okay, so let's say we've got this stretched cluster set up. How do we make sure that our data stays consistent across all these different locations? I mean, that seems like a pretty tough challenge.
Well, that's where this really clever concept called node quorum comes in. Think of it like a voting system among the nodes in your cluster. And you usually have an odd number of these nodes, right, like 3 or 5. And for the cluster to stay up and running, a majority of those nodes have to be active and talking to each other.
So it's like a majority rules kind of thing.
Exactly. And that prevents something called a split brain scenario,
Yeah.
where different parts of the cluster start operating independently and you end up with data conflicts.
Right, because you wouldn't want different versions of the same data floating around, right? That would be a nightmare.
A total nightmare. And
Yeah.
what's really cool about this quorum thing is that even if the connection between your main sites goes down, as long as most of those quorum nodes can still communicate, the whole system can keep running.
Oh, that's pretty impressive. So even with a major outage, things can keep ticking along.
Exactly. And that's exactly what you want in a high availability environment. You want to minimize that downtime as much as possible.
So node quorum keeps the nodes themselves in check, but what about the file system itself? How do we ensure that like the files and directories are consistent across all these sites?
Well, for that, you have something called file descriptor quorum. And file descriptors, they're basically these little bits of metadata that tell you all about your files, your directories, the whole state of the file system, really.
So it's like the instruction manual for the file system?
Yeah, pretty much.
Yeah.
And in a stretched cluster, those descriptors are copied across different failure groups, which adds another layer of redundancy. The rule is you need a minimum number of these descriptors to be active at all times to make sure that losing one part of the system doesn't bring the whole file system down.
Oh, that makes sense. So we've got redundancy at the node level and redundancy at the file system level. That's pretty thorough.
It is, and it's all about ensuring that data is accessible and consistent no matter what happens.
Okay, so we've got a good grasp of the concepts. Now let's get our hands dirty and talk about how we actually set up a system like this. Our source material mentions using an installation toolkit, which sounds pretty handy.
Oh yeah, installation toolkits are a lifesaver, especially when you're dealing with something as complex as a stretched cluster. And Stonefly, they've got this down to a science. Their solutions are designed to be as easy to deploy and manage as possible.
So what does the toolkit actually do? Does it, like, walk you through the whole process step by step?
Pretty much. It takes care of a lot of the heavy lifting. Things like installing software packages, configuring the initial network settings, setting up the basic structure of your cluster. It even handles things like adding information about your network shared disks, which is how you tell the system where the storage is.
And to make sure those disks are assigned to the right failure groups, right? So your storage is spread out properly from the get-go.
Exactly. The toolkit really streamlines the whole process and helps you avoid a lot of potential headaches down the road. And speaking of avoiding headaches, once the system's up and running, you'll probably want to use a graphical user interface, or GUI, to manage it all.
Oh yeah, GUIs can be super helpful for managing these kind of complex systems. It's much easier to visualize what's going on than staring at lines of code all day.
Right, and a well-designed GUI, like the one offered by Stonefly.com, gives you a really user-friendly way to monitor the health of your cluster, manage your file systems, configure all sorts of settings. It's like having a control panel for your entire data infrastructure.
Makes sense. And the documentation mentions accessing this GUI through a web browser using HTTPS, so it's secure and you can manage it from anywhere.
Yeah, that's pretty standard practice these days for remote management. It's secure and convenient.
Now, something I've been wondering about is how users and applications actually access data when it's spread out across all these different sites. I mean, how do you make sure it's seamless for them?
Yeah, that's a really important consideration. And the documentation talks about using both native protocols, which are specific to the storage system itself, and standard protocols like NFS, which is Network File System.
So some clients might connect directly to the storage system, while others might use a more general purpose protocol.
Right. And often, you'll use a load balancer to distribute those client connections across different protocol nodes at different sites. It's all about making sure that client connectivity isn't tied to just one location.
That's smart. So if one site goes down, the load balancer can redirect traffic to another site, no disruption for the users.
Exactly. And of course, you want to make sure you've got proper file authentication services in place, especially when you're using standard protocols like NFS. You don't want just anyone accessing your data.
Absolutely. Security is paramount. Now, let's get to the part everyone's probably been waiting for. What happens when things go wrong? And let's start with that tiebreaker quorum node we talked about earlier. What if that fails?
Okay, so the good news is that with quorum, it's all about majority rules. So in a typical three-site setup where you've got that tiebreaker in a third location, losing that one node doesn't actually affect the overall quorum of the cluster.
Because the other two sites still have a majority of the quorum nodes, right?
Right. And the tests they did showed that client traffic, whether it's using the native protocol or something like NFS, it just keeps on going. No interruption. The cluster stays operational.
That's reassuring. It's good to know the system can handle that kind of failure without breaking a sweat. But what if something more serious happens? Like, what if an entire data center goes offline?
Now, that's a bigger issue. Because if a whole data center goes down, you're not just losing quorum nodes, you're probably losing other critical components too. But the key question is whether the remaining data center can still maintain quorum.
So if the surviving data center can still talk to that quorum node in the third site, it's still good, right?
Exactly. The cluster might switch over to a node in the surviving site, but the file system stays mounted and accessible. And the tests showed that client traffic was mostly unaffected. There might be a tiny pause for some services, but overall, things keep running.
Wow, that's pretty impressive. It can handle an entire data center going offline. That's the kind of resilience you want. Now, what if it's the other data center that fails? Is there any difference?
Nope, it's basically the same outcome. As long as one of the main data centers and that third quorum site are still connected, the cluster can keep going. Client access remains unaffected, everything's good.
Okay, that makes sense. It's a symmetrical design. Now, this next scenario sounds a bit trickier. What if the two main data centers lose connection with each other, but they can both still talk to the third site? Wouldn't that cause problems?
That's where you run the risk of that split brain scenario we talked about earlier. Each data center might think it's the only one in charge. But thankfully, the quorum rules are designed to prevent that from happening.
So how does it decide which data center is the real one?
It comes down to which site is currently hosting the active cluster manager. That's the component that's calling the shots, so to speak. And the site with the cluster manager will usually stay active while the other site gets kicked out of the cluster to avoid conflicts.
Ah, so it's a way of preventing two different versions of the truth from emerging, and the test confirmed this, right?
Yeah, they showed that the nodes in the data center without the cluster manager were forced offline. But client access from the surviving site continued without any problems. So the system essentially self-corrects to maintain data consistency.
That's pretty neat. It's like it has a built-in safety mechanism. Now, what if only one of the main data centers can talk to the third site after they lose connection? What happens to the isolated one?
In that case, the data center that can still communicate with the third site will form a quorum and stay active. The other one, the isolated one, will be expelled from the cluster because it doesn't have enough quorum nodes to stay in charge. It's all about maintaining that majority.
Makes sense. It's like being voted off the island. Okay, last failure scenario. What if all three sites lose connection with each other? What happens then?
That's the worst case scenario, really. If none of the sites can communicate, then the whole cluster loses quorum. And when that happens, all the nodes in both main data centers are expelled and the file system becomes inaccessible. It's like the whole system goes into lockdown to protect the data.
So basically, everything grinds to a halt until the connections are restored. That's why having a solid network infrastructure is so crucial.
Absolutely. And it's also why having alternative quorum mechanisms, like those offered by Stonefly, can be incredibly valuable. They provide a way to maintain availability even in the face of these really extreme network outages.
Okay, so we've seen how a stretched cluster handles all sorts of infrastructure failures. Now let's switch gears and talk about AFM-based disaster recovery, or AFMDR. How does this differ from the kind of real-time mirroring we've been talking about?
So AFMDR is a bit different. It's more about asynchronous replication between a primary site and a secondary site. Think of it like having a backup site that's constantly being updated, but not in real time.
So it's more like having a safety net than a mirror image.
Exactly. And the primary site can keep working even if it loses connection with the secondary site for a while. Once the connection comes back, it'll catch up the secondary site with all the changes.
So it's a more forgiving approach, I guess. And Stonefly, they use this kind of asynchronous replication a lot in their disaster recovery solutions, right?
Yeah, it's a very common and effective approach. And the cool thing is that it replicates not just the data itself, but also important metadata like file attributes and even rename operations. It's all about maintaining consistency.
But some things aren't replicated, right? Like certain high-level file system settings.
Right. Things like quotas and replication factors, those aren't typically replicated with AFMDR.
Right.
But to make sure you have a consistent copy of your data on the secondary site, you can use snapshots.
Snapshots, those are like frozen points in time, right?
Exactly. And how often you take those snapshots determines your recovery point objective, or RPO. That's basically how much data you might lose in a disaster.
So the more frequent the snapshots, the less data you risk losing. Makes sense. Now, let's talk about failover. How do you actually switch over to the secondary site if the primary one goes down?
Well, that's called the failover process. Basically, you activate the secondary site, make it read-write enabled, and redirect all your applications and users to that new temporary primary site.
And the goal is to switch to the most recent snapshot, right? To minimize data loss.
Exactly. You want to make sure you're working with the most up-to-date copy of your data. And once the original primary site is back up and running, you can do a failback to restore normal operations.
So failover is like hitting the emergency switch, and failback is getting things back to normal. And AFMDR, it's designed to make this whole process as smooth as possible, right?
Exactly. The goal is to minimize downtime and get your systems back online as quickly as possible.
Okay, so let's dive a bit deeper into the setup process for AFMDR. What are some of the key things to consider when you're configuring this kind of disaster recovery solution?
Well, the first thing is that you need both your primary and secondary clusters up and running before you even start thinking about AFMDR. Then you need to decide which file sets you want to protect and replicate, and you set up the AFMDR relationship between those file sets on both clusters.
So it's not like everything is automatically replicated. You choose what's important.
Right. You prioritize the data that's most critical to your business, and then you need to choose the transport protocol you want to use for replication. AFMDR supports both the native NSD protocol and the more standard NFS protocol.
And what are the trade-offs there?
Well, NSD is generally faster, but it needs a stable and low-latency network connection. NFS is a bit slower, but can handle network hiccups better. so it depends on your network and your performance needs.
So it's a balancing act between speed and reliability. And Stonefly, with their experience, they can help you figure out what's best for your situation, right?
Absolutely. They've got the expertise to assess your needs and recommend the optimal configuration.
Okay, so you've got your clusters set up, you've chosen your file sets and your protocol. What else is there to consider?
Well, you need to choose your AFM gateway nodes. Those are the nodes in your primary cluster that are responsible for pushing the replicated data to the secondary site.
Ah, so they're like the messengers carrying the data back and forth.
Exactly. And for high availability, you usually want at least 2 gateway nodes. More if you've got a heavy workload or lots of file sets to replicate. And there are some parameters you can tweak to optimize their performance.
So it's not just a set it and forget it kind of thing. You need to fine tune it for your specific environment.
Right. And finally, to actually activate AFMDR for a file set, you run a command on both clusters. It's like flipping the switch to turn on replication.
Okay, that makes sense. Now, the documentation mentions a simulation they did where they took down a primary gateway node. What happened there?
Well, when a gateway node fails, the system is designed to automatically recover. It detects the failure and switches over to another healthy gateway node.
So the replication process doesn't just stop, it keeps going, just with a different node in charge.
Exactly. And the tests showed that client applications were unaffected. There might be a brief pause in replication, but that's it. And once the original gateway comes back online, the system might switch back to it.
So it's like a self-healing system. It adapts to failures and keeps things running smoothly.
That's the goal. And that's the kind of resilience that Stonefly builds into its solutions.
Okay, last topic. Failover and failback using role reversal. What's that all about?
So role reversal is a newer and more efficient way to do failover and failback. The main advantage is that it cuts down on the downtime you experience when switching back to your original primary site.
Because traditionally, you'd have to manually resync a lot of data, right?
Exactly. And that could take a long time, which means your applications would be down for a while.
Hmm.
But with role reversal, you essentially swap the roles of the primary and secondary sites.
So the secondary site, which was the stand-in primary, just keeps being the primary. And the original primary becomes the new secondary.
Right. And for a planned failover, you first make sure both sites are in sync. Then you unlink the file set on the original primary, promote the original secondary to primary, and relink them in their new roles. It's like a choreographed dance.
And the documentation walks you through all the steps, right?
It does. It even tells you how to handle any files that might not have been replicated properly. And the tests showed that failover and failback using role reversal was super smooth. Clients could immediately start writing data to the new primary.
So it's like a hot swap. You switch sites without missing a beat.
That's the idea. And Stonefly, they got this down pat. They help their clients implement role reversal to make sure their disaster recovery process is as painless as possible.
All right, so let's wrap things up. Today, we've explored how to build incredibly resilient systems using multi-site high availability and disaster recovery solutions. We talked about stretched clusters, quorum mechanisms, and all sorts of failure scenarios. And then we dove into AFM-based disaster recovery with its asynchronous replication and that cool role reversal technique.
And it's important to remember that these concepts are not just theoretical. Companies like Stonefly.com are putting these ideas into practice every day, helping businesses protect their data and keep their operations running smoothly, no matter what.
Absolutely. Stonefly's been a pioneer in this field for over 2 decades. They offer a comprehensive suite of solutions, from SAN and NAS to cloud and AI-powered security. They're the real deal.
And if you want to learn more about how Stonefly can help you build a truly resilient IT infrastructure, visit their website at stonefly.com or reach out to their team at sales@stonefly.com.
They're incredibly knowledgeable and helpful. Now, as we wrap up, I want to leave you with this thought. The ability to seamlessly transition operations between sites, like we saw with role reversal, it's a real game changer for disaster recovery. It's no longer just about backups. It's about active resilience, about being able to bounce back from anything.
And that brings up an important question. How can you apply these principles of multi-site architectures to your own organization? What are your biggest challenges, and how can solutions like those offered by Stonefly help you overcome them?
This deep dive is just the beginning. There's a whole world of knowledge and expertise out there, so keep exploring, keep learning, and keep striving to build systems that can withstand anything.
Because in today's world, data is everything, and protecting it is no longer optional, it's essential.
Thanks for joining us on this deep dive, and a big thank you to Stonefly.com for making this episode possible. Until next time, stay curious and stay resilient.